Coloring is an easy activity. It's so easy that you tell your kids to do it when you don't feel like raising them at the moment. Give them something to distract themselves. They'll figure it out. Maybe they'll eat a crayon or two, right? But at the end of it, they'll probably do it right. They're going to color in the page. They'll be left with maybe a cute image, and you might hang it on your fridge. I can't remember the last time I sat down and colored a coloring book, but as far as I can remember, it wasn't very confusing, and I always sort of knew how to do it. I was never ever taught what the algorithm for coloring is. I just kind of looked at it, colored within the lines, and it worked, right? I got an image at the end. And so I'm making a puzzle game about drawing right now, and it turns out it is a little more confusing, right? You see this sort of image here that I've created with a very simple node setup in this math-based drawing game. And I wanted to add a fill node. And I thought, okay, if kids can do it, how hard can it be? And so I got down to it and I was like, okay, I have no idea how to color this in, right? And so I want to go into some of the work that I've been doing to get to the point where I'm at now, where I can generate these very cute, nice mosaics um, and properly color them in. And so the first thing I did is look at, I guess, how real life ones are colored. So I have some real life mosaics here. And when you see them, you can see what I mean, right? There are the lines that separate these smaller, distinct shapes, whether they're made of stained glass and they're in a religious setting or made of small stones. What you're seeing is a small, dense collection of tiny shapes that break up a larger shape. The coloring, of course, is not as random as the ones I'm making. It's much more deliberate and it's mimicking a subject material, but it does still, regardless, match the form factor of what I'm trying to also solve. So the first question that comes to mind is, well, how would I color it? So when you look at an image like this, where it's a fractalized heart, I think everyone's brain, since they were 5 or 6 years old, just sort of intuitively understands how to color it in, right? Obviously I'm just on a website here, so I can't fill it in, but like you want to fill each shape within its smallest section a certain color, and then you fill another one, and you know you just do that, and there's not much thought behind it. I mean, I couldn't even tell you, like, if I had this in a physical coloring book, why I'm coloring each space the way I am. I can tell what the smallest shape is. So you have to ask yourself, how am I telling? How do I know what the smallest shape is? And so I guess that's what I wanted to discover, is that how do we look at this sparse set of lines, right? They all sort of are just points at the start and end. And how do we determine, well, what these smallest shapes are, right? How do we determine what the polygons that we should be flood filling are? So I want to run through what the data is doing a bit. And so this is essentially what we're delivering to the fill system as data currently, right? We have what is currently the definition of the data is a collection of segments. So we have, I guess I'll start the segments on the canvas, right? Because they're bounded to a box in the image. So you have 4 segments that bisect the canvas, right? And they start and end at these points. And then we also give the filler a set of segments that defines the bounding box. So the shape of the data as it stands at the very start is a bunch of multi-segment lines that are defined as collections of ordered points, right? And you have a few of those. And so you can't do anything with this, right? And I'll link some of the studies I read in the description, but it turns out in order to do basically anything with a computer, you need more data, right? And so the first thing we're going to compute, and this is the same first step that all of them compute, is we're trying to make a graph. And so a graph needs more points and it needs directed edges. right? Because right now, if we wanted to make a graph out of these segments that are available, you'd create one big square. And so for those of you who went to college for computer science, not so valuable these days, but if you did, you'll remember algorithms where you studied like Dijkstra's, A star, the traveling salesman. All those problems are related to traversing graphs. And it turns out this problem is also traversing a graph. And so the first step to making the graph is getting the collection of, like the true collection of points, right? So we want to compute the intersection points. And so where does each line intersect each other line? And we're going to split those segments at those intersections into more segments, right? So let's take the bounding box, for example. This top segment here is intersected by two lines at these points. So now we're left with three segments at the top. And so we're going to do the same thing for every single segment along the way. And there are some optimizations for this that you can make, like, quantizing points, using bounding boxes to determine if you should even intersection test. But at the end of the day, once you've computed it however you compute it, you have a set of points that defines intersections, and you have a set of edges that you can then use to define the graph. But that's not quite enough information. We want to also give these edges some direction, right? And the direction is both, but you want to give the walker some information, right? At each edge, right? Where can it go? If, for example, the parser started here, what are the options? Well, it has an outward edge here and an outward edge here, and we're going to apply the same logic to every point. Okay, if we go to, I don't know, this point next, what are its options? Well, it could go to this one, it could go to this one, or it could go this way. And, you do this for every single point, and you get what is known as a set of half edges, because you'll notice that it's like we took every edge and split it into half, right? So we take this tiny edge here, and you get this half that goes south, this half that goes north. So every single edge turns into a half edge of itself. And you give that information, and now you can define some sort of walker, right? Because if you give it an arbitrary starting point, it can then define where it's going to go. It can go south, then it goes, northwest, then it goes a little more northwest, and it could go back, right? And so now that we have a structurally walkable graph, you can define how to walk it, right? And so we'll define the walker. Let me remove these lines so it's a little more parsable. Um, so arbitrarily speaking, we can start our walker anywhere, but we need to walk this graph, and we're going to find every unique polygon. If you've ever been on Facebook, you'll see these sort of puzzles that confuse older ladies and older dudes online, and they'll post comments with all sorts of wrong answers. But like one example, would be like, you know, how many rectangles are in this image? Well, an imbecile might say, oh, well, there's one, two, three, four, five rectangles. But that leaves out the longer bottom rectangle that is divided into two, leaves out the longer top rectangle here, leaves out the really long top, the really long bottom, the full rectangle. Point is that some of these polygons on a first glance are easy to spot because they are the smallest one, and they're not containing any other sub polygons. But then some polygons are containing other ones within them, including the final shape, which contains every polygon. And so as we walk, we're going to get a selection of polygons. Some of them will contain others, some of them won't. So let's get a small sample set here. We'll walk starting at this corner, right? We have here, we have two options now. We can go here or here. And let's pretend there's no more options, but then we could go here, same graph, or here, here, here. And so I just did a bunch of walks at once, right? But this leads us to a set of polygons like this. You have this small rectangle here. I guess it's not really shaped like that. Let me, and then, and then, and then you have the same thing, but it contains this tip. You have the same thing, but it contains both tips, and it's just a triangle of sorts. And then you have also within these, and we'll pretend that the parser started and grabbed these as well, starts here, grabs those. You also have these tiny tip triangles, I guess. And so when you have, let's say this is the full set of polygons, right? When you have this full set of polygons, you need some criteria to say, okay, well, this one's bullshit. We don't want that, and we don't want that either. And it turns out the criteria is pretty simple. Number one criteria is you can't fill an open shape, right? It has to be closed. What is a closed shape versus an open shape? Well, a closed shape would be anything like sort of this, where there is a missing edge, right? This edge here is not visible, therefore the shape is open. If you tried to fill it, the fill could escape, right? And then you have closed shapes, which are any shape where it's closed, right? Um, and so that's the easiest criteria. In my example, there would be no open shapes, but if there was a spurious line right here, right, you would come into some open shapes. Um, and so when you have closed polygons, you have another few things you want to know, right, about each polygon. And we collect this data along the way. We give it a perimeter, an area, a centroid, which is defined by its bounding box. But the important number for at least selection is the area. You can't fill something that has no area or negative area, right? And so when you have these polygons that are parent polygons and child polygons, meaning that there are polygons within the polygons, right? So this one here has literally 3 child polygons. This one here has 2. You'll notice that, well, if we were to take A here, the area A, area B, and area C, and you were to subtract them from their parent polygons, subtract here, subtract C, A. Well, the area of this polygon is A plus B plus C. Subtract all of those, it's 0. So we know that polygon is no longer in the running to be a smallest polygon. Same for here, right? Subtract A, subtract B. This is a 0 area polygon. So at the end of it, you get this sparse grid of intuitively, I would say, intuitively smallest polygons, and that's when you do the filling, of which when you fill, at least currently, there is a bit of a selection method for color, but at the end of the day, it is just colors. And, you get a sometimes cool image. In this scenario, it is just a bunch of triangles of some varying colors, but it was so easy for the fill tool and so easy to see, but that's all the work that really goes into telling the computer exactly what to see. All right, so here we have a debug video I recorded of a bunch of objects in Engine that I separated. I don't know why I'm not doing it live, but it just is what it is. So the first thing I do here is I separate out what the initial given set of segments to the filler is and the intersection commuted segments. So you see here in this little cross here, this is the only example I really dive into, you have these 2 segments. They are completely whole. That same cross, like we detailed, is now 4 segments. And so that was the first step that I showed earlier. And so now you have these set of vertices, right? And these vertices have these half edges between them, of which you can see there are all these doubly sided lines, right? With multiple heads and vertices at each of the points. I removed the background for some clarity, and I want to show what a half segment is. You see here, there's the going north and the going south line, similar to here, how you can see, what's going on there. And so I'm going to hide all that now, and you're going to see the final resulting set of polygons, which is this left one here. It's got a funky thing. This is captured by a fallback. And then you have every other polygon here as we break it apart, including the background one that I moved. This is a different clip. I should ignore it. But point is that the entire process I just showed is basically exactly what's going on as I construct these polygons in Engine. So as far as color selection goes, I'm not doing anything as complicated as the mosaics of old, right? I have some rules here for filling, right? I can do what I would call a parity fill, where there's even and odd, and then the mosaic fill, which I think is much cooler looking. And so, you'll find that like the stone mosaics in real life are very, earthy tone heavy, and then like very, the religious stained glass mosaics, those, they're very saturated values. Um, but I'm not really limiting the palettes. I'm letting the palettes be influenceable. And this is all for a project I'm making, which will end up being an art based or a math art based puzzle game where you use, signals, you wire them together to create an output image, and you're trying to match the output image to an expectation, right? You'll get a dashed line potential image, and you are trying to match to that, and that is the puzzle. And I'm trying to create a very cool sandbox tool set that lets you create just about anything. You have this larger stained glass circle thing here. You have, especially the lines are a little hard to visualize, but let me show this one with the lines. Let me make them not white anymore if I can, or actually I'll make them thick, I suppose. And so, you can see there is a lot of drawing going on here before the filling. Of course, it looks better. The mosaics, at least in my opinion, look better with white lines, or if you just, disable the line thickness entirely and make them invisible. But the hope of what I'm making is that you'll be able to make cool images, and I'll make interesting puzzles where you have a larger canvas, right? And so, if your canvas is, you know, a bunch of smaller images all added together, you can create a cool scene. And the puzzle will be to, you make a house in this square, make a sprawling hill in the background, and then once you've solved all the puzzles, it'll come together, it'll all get drawn and say, great job. And along the way, I had to learn a lot about the whole subject of this video, polygonization, to make this project possible. And so I just wanted to show that off as a step I'm having along the way, and I hope it was interesting to someone. I hope maybe you learned something, read the studies for a more intelligent person to explain these things to you. But yeah. Uh, oh, bye bye.